Welcome to Maths with EJD. In this video, I continue to talk about SciPy, and today the focus is on the SciPy.Stats Module, right? As you might already know, in case you've seen some videos before now, all the notes I use for this scientific computing with Python, you can find a link to them in the description box, so you can actually get to download the notes, so you can practice hands-on, so you can follow, just the way I go on, so you can actually, interact better with these videos. All right, and of course, if you have not subscribed to this channel, you want to do that straight up, and of course, hit the notification bell so you don't ever miss out when a new video is released. Okay, so let's go on to talk about the SciPy.Stats module. The SciPy.Stats module, of course, is a powerful library in Python, and it is used for statistical analysis and probability distributions. It provides a wide range of functions and classes for various statistical calculations, hypothesis testing, and generating random variables from different distributions. So, of course, statistics is a very important part of so many people's life. So if you're looking for a Python library to help you get around statistical stuff, of course, SciPy is the place, and the stats module is what you need. So let's explore the various functions we can find here. First of all, let's talk about random variables. Sometimes it becomes important to generate random variables, or you just want to get some numbers randomly and all that. So SciPy.Stats module is excellent for doing that. For instance, if you want to generate random variables, you can generate random variables that are uniformly distributed, normally distributed, or that are exponentially distributed, right? So if you look at this first cell, of course, the first line, okay, let me put the line number so we can easily reference the numbers, okay? So in line 1 of this first cell, now you see from SciPy.Stats, import uniform, norm, and expon. Now, uniform is for uniform distribution, norm is for normal distribution, and expon is for exponential distribution. And of course, for uniform distribution, see what you have here. Uniform distribution, I call that, the variable name is data1. So I just say uniform.rvs. So RVS is like the keyword here because we are dealing with random variables. So, but then what kind of random variables? It is uniform.rvs. I want it to be like 100 data points, 100 data, all right? And of course, you print the data here so you can visualize. So this print here is blank. So so to have space, so you can, before you go for the normally distributed random variables, and then of course this is exponential distribution. So if you check the note that you want to change that to exponential, and of course you can see that the keyword there is expon for exponential.rvs, that's random variables. Here it's norm.random variables, and the first one, data1, is uniform.random variables. So if I run this now, you just discover that you can get random variables. So you look at the first set now is uniformly distributed. The second one is normally distributed. And the third one is exponentially distributed. And of course, because it is random variables, right? If you run it again, if you keep running, you keep getting different sets of data. So it is very good for, for experimenting, right? Maybe you're trying to work something out. So you can try with different different variable values, so you can see if what you're experimenting with is working or not. So that goes. Let's move on to, so we've seen how SciPy.Stats module can help with random variables with functions like uniform, norm, expon, and so on and so forth. All right, so let's talk about probability distributions now. There are all kinds of probability distribution, and they are broadly classified into continuous distributions, where you have to deal with numbers that are not discrete, numbers that you cannot count. Maybe you have something like maybe from maybe 1.5 to 1.7, something like that. You can't really count the points in between because there are infinitely many points in between. So that's continuous distribution. And of course, you also have discrete distribution, and they have their associated probability distribution. So talking about continuous distributions, for instance, you have normal continuous distributions, you have exponential continuous distribution, and you also have chi-square. Chi-square is particularly good for what is it called now? It's particularly good for categorical variables. For so if you have an idea what that is, as if you have done some statistics courses, right? All right. So here, let's look at the normal distribution and see what we can get. So here, talking about you want probability distribution that is normal. So in line 4, you have data, that's the variable name, and you have normally distributed random variables. You already saw the essence of this, right? Normally distributed random variables. That's the first thing I think it's the second set of the variables we generated here is normally distributed. So we are bringing that kind of idea here to say that we want normally distributed random variables like that. And here, of course, for normal distribution, right, this LOC is actually talking about the mean. So mean 0 and standard deviation 1. That's what the idea is for normal distribution. And the size is 1,000. That means you are generating 1,000 random numbers. And that is what we want to print here. So, and of course, for the number now, okay, if you look at line 9, so whatever, so the num.fit data, that fits the distribution to data. So this data you have now is going to be fit to the normal distribution, normal distribution like that. And you can extract the mean and the variance of this. So this line 11, and okay, if I spread this apart, right? So now lines 11 and 15 will give you the mean and variance respectively from whatever you get from line 9. So I just run that and you see, first of all, the whole data is like 1,000 and it is normally distributed. So that's just the normally distributed data first. So the second thing is for all of that data, the mean is minus 0.0009, blah, blah, blah. And then the variance is 0.9 this. But because the data is randomly distributed, because the variables are random, so if I run it again, you're going to get another set of data so that the mean again will be different. So now you see the mean is 0.03191, 3191, and of course the variance is 1.0384. So if I run it again, so anytime you have normal randomly generated variables like that, the values keep changing. So that's for normal distribution. Of course, if you want exponential distribution or chi-square, you can do that. I think along the line, we're going to see something about chi-square also. So that's for continuous distributions. How about if we talk about discrete distributions? In this case, we're talking about distributions that involve countable numbers. Like you can tell the numbers apart. Like you can say 1, 5, 7, 8, like that. And it's not like all these points. So it doesn't have decimals most likely. All right. So let's say so the possibilities you have in this case would be like Poisson distribution, binomial distribution, or geometric distribution. For this particular example, our focus is on binomial distribution, where we use the binom keyword, the binom function with the random variable. So it means here we're taking 10 trials and the probability, and P is 0.5, probability of success is 0.5, and the size is 1,000. All right. So I'm printing the successes so you can see what it looks like. And then I'm printing the mean and the variance. Of course, all of this, if you have a statistical, you can check the statistical theory backing all of this. Or for instance, you want to know that the mean is 10 times 0.5. So we are always sure that the mean is always going to be 10 times 0.5, which is 5. So whatever happens, the mean is always going to be 5. Though the variance can always change because this is for binomial distribution. So 2 possibilities happening in each case. Okay, so I run that now. See, so because it's discrete, right? You have all these numbers that are whole numbers that you can actually count. Okay, and you can see that the mean is 5.0 because the mean is for binomial distribution is always the number of trials, n equals 10 times probability 0.5, and that's always 5 no matter what we do. So if I run it again, take note that this is 479. That's the first set of the three numbers we have first. So if I do it again, now see it's 638, but the mean will always be 5. The mean is still 5 and the variance is still 2.5. So let me try another one. Looks like okay, the mean and variance, they are fixed values. Okay, that's for discrete distribution. So you can try the same for Poisson. You can try for geometric distribution also. So and of course, to do that, all you just need to do is change binom to Poisson or to geom as you have it up there. Okay, let's talk about statistical functions. Statistical functions. One of the things we do with statistical functions is we get descriptive statistics like descriptive statistics simply talks about one value to represent the whole data set you have, right? So you have things like mean, minimum, maximum, variance, skewness, kurtosis, and so on and so forth. All of this have their descriptions, their definitions, even mathematical definitions in the theory of statistics. So for instance, from SciPy.Stats, you can now import describe and norm, right? So of course, we also need NumPy here because we have some. Don't forget that SciPy is built on NumPy because we need arrays. So the arrays are borrowed from NumPy, basically. So that's why we have NumPy coming up here again. For instance, generate some random data from a normal distribution. So, and we say data now, and we are getting normally distributed random variables with mean 0 and standard deviation 1, and the size is 100 in this case. So we want to see what the data looks like. And then you want to calculate the descriptive statistics using describe. So you have DESC equals describe data, and then you can now print DESC. So this describe now is what helps you to get all the possible distributions. So, and of course, if you print, let me do something. Okay, if you print the describe, you see all the possible things it can give you, but these ones are now giving you the specific values of those things. So you can get the mean, the minimum, the maximum, the variance, the skewness, and the kurtosis, like we said. So if you run this, see what you get. So the first set of data are the normally distributed random variables. So all this now normally distributed, and the mean is 0, while the standard deviation is 1, And then of course, for this print in line 12 is what gives you the second set of things. So if you look at the described result now, it's giving you number of points. Now you have 100. So the minimum and the maximum values are these two, minus 2.88, 2.70. And that's why you see minimum and maximum down here are like that. So you see the mean also is minus 0.02. So that's the mean you have here. So variance is 0.98. That's what you have here. Skewness is minus 0.04. Kurtosis is like minus 0.09. And that's all you have here. And because variables, the data is random, so if I run it again, the values change, right? So you can see the values have changed now. So all of the values have changed. So the max and mean have changed. So the thing is, if you keep running this, you keep getting different values because they are randomly generated variables like that. Okay. So that's about the one aspect of statistical function, which is descriptive in nature. How about if we talk about hypothesis testing? We do different kinds of hypothesis testing depending on the kind of data you have. So one of it is student t-test. Then you have ANOVA, analysis of variance. You have the Kolmogorov, Smirnov test, and so on and so forth. So you can do all of this, by calling the SciPy.Stats module, and from it you can import whatever you want. Like if you want t-test, you do t-test _ IND, and then F1 way, that's more like if you want to do ANOVA, and you have KS2 sample or something like that. So, but here our focus is on the student t-test. Usually statistics, right? You do the student t-test if you have data that is if you have very small data value, right? Because if you have a large data set, right, it's tending towards normal distribution, so to speak. All right. So here, again, group 1. So here it's like we're comparing between two groups, one to test hypothesis. And of course, the usual null hypothesis is there is significant, or better still, there is no significant difference between the two groups. That's what that is. Maybe you take measurements like, okay, you have 100 people in two different groups, and you want to compare maybe their heights. So maybe you take, I'm just making that up. I'm just trying to explain that. Maybe in group 1, all the people there, you have their height randomly generated, and group 2 also like that. Of course, in real life, right, if you have your normal data, you can just import it here and do the same analysis and you get your result. But here we are generating random variables to carry this out, okay? Because it's more convenient in this case. But if you have your actual data, you can use this kind of idea for your hypothesis testing. So here, you have group 1, normally distributed random variables, 100 of them each in group 1 and in group 2. So here we are visualizing group 1, the first print. The second print is visualizing group 2. And of course, the other print now is printing the test statistic. So the test statistic is actually the value you get, when you do your testing. And of course, when you now compare that with a particular standard value, then you can know what to make up your mind on, right? For instance, if the test statistic is less than a particular value or something like that, those are the kind of things you do. But of course, p-value is a very perfect way to know, to make a decision about whether the two groups are the same. So null hypothesis, there is no significant difference between the two groups. The alternative hypothesis is there is significant difference. And if the p-value, most of the times, if you get a p-value greater than 0.05, then so the null hypothesis is satisfied. But if it is greater than 0.05, then it means the alternative hypothesis is satisfied, meaning that there's significant difference. So let's do this. We can keep doing it and get different results because it's random. The two groups are randomly generated. So if I do this now, this is group 1 up here, this is group 2. The test statistic here is minus 3.42. Interestingly, the p-value here is 0.00075. So it means that based on this data we have in group 1 and group 2, there is no significant difference between these two groups because our p-value is less than 0.05. 0.000 zeros is less than 2 zeros, 0.05. In fact, 1 zero, right? 0.05. So, and here it's so there is no significant difference between the two groups. That is what this p-value tells you. So if I run it again, let's see what we get. I run it again, another set of data. Now you can see the p-value is even smaller, like 7 point blah 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 times 10 raised to minus 8. So there's still no significant difference, right? No, am I getting it wrong? If the p-value is less than 0.05, does it mean there is significant difference? Okay, yeah, it means there is significant difference. Yeah, I think so. I mean, you can check to confirm that, but I mean, that's one of the rules like that. I wonder why I'm not very sure about that right now. So, I mean, it's showing that there's always that significant difference because the p-value is far less than 0.05. Okay. So, all right. So talking about statistical models now, statistical models, you talk about linear regression. That's one thing. So of course, the idea of model basically tells you that you want to get like an equation with which you can always decide about two data sets. So the first data set, you have some, you have X, that's maybe whatever X is, right? You have 0, 1, 2, 3, 4, and then you have Y, you have 0.0, 0.8, and all that. And then you want to make a regression line, from this data. So such that you can now have that line, you can always now use that line to estimate for other values. So so we have this X, we have this Y now. And of course, to get an equation, you need Y equals MX plus C. M is the slope and C is the intercept. And once you get those two now, you can see line 8 and 9 here talk about slope and intercept. And of course, the p-value tells you about the significant level, the level of significance, extremely important. Okay. So if we click this, if we run it, see what we get. So first of all, we get the slope. So if you want to write this equation now, it will be like y equals the intercept, y equals 0.66. Like y. Okay, well, okay, this is not random, so we can actually make a decision about it. So okay, or I can actually create this under and maybe go markup, So the line for the linear regression here is y equals mx, that's 0.66x, plus c, the slope, that's minus 0.23, like this. So with this line now, you can always fix your value and estimate, okay, if someone, okay, well, I think the second example is going to explain that better. All right. So you have y equals 0.66x minus 0.23. So with this line, you can say, okay, if x is 5, you can know what if x is 5, for instance, right? That's like 0. If x is 5, I think that should be 3.3. So 3.3 minus 0.23, that gives you something. So that tells you that when x is 5, y is some value close to 3, like that. Okay. All right. So here now, I'm actually using the idea of maths score. So I'm assuming, so we have like 10 students and they took tests in both maths and physics. So, okay, So you have the math score to be 70, 92, 45, and all this. You have the physics score to be this. Sometimes with this kind of data, you can now say, okay, if this is the data, right, you can actually fit a regression line to it, such that if you know the value, the score of a student, let's say the x-axis is math score and the y-axis is physics score. So with the math score, you can guess what the physics score is, and with the physics score, you can guess what the math score is. So okay, in the notes now, you're going to see a mistake, because if I run this now, it's going to give me the result from the previous case, because those are the x and y. So it's from the previous situation, which is not correct. So here now, for x, I should put math score. So I should have math score here. So in case you have the notes without me changing x and y here to math score and physics score, please remember to change that, okay? So if I run this now, it gives me a different set of results. So that the equation now is going to be y equals 0.12. So it means that physics score, which is our y-axis now, physics score is going to be equal to, okay, I think I should even write that out for easier understanding. So it means that physics score, so a student's physics score is always equal to the slope 0.1298, 0.1298, then multiplied, so let me say times the math score times the math score. Did I say, oh, it's math score here, times math score, all right? And the intercept is plus 56.6353, okay? So if I do this and I put it in markup, right? Markup. So, see what you get. Okay. I think I need to do something about that. My physics score. Okay, let me say this is text. Or should I say text? Let me just say, okay, let me do it this way. So we can say that, let's do text and say physics score. I can write this in full. Physics score, all right, is equal to 0.1298 times another text. Then I have maths score, maths score, all right, as a text like that. So if I do this, see what you get. So it means physics score would always be equal to 0.1298 times math score plus 56.653. So it means that if you know somebody's math score, just substitute it here, and you can get the estimated physics score. Of course, if you know the physics score, so you can put the value, then just subtract 56 from it and divide by 0.1298, and it will give you the math score. That's how you fill lines of regression. So you cannot estimate that, okay, based on this line now, if somebody has like 100 in maths, what is the person going to likely get in physics? So having 100 in maths would mean that the person will have 0.129 times 100, right? That is 12.9. That's like roughly 13. So 13 plus 56. 13 plus 56, that is 69. So, or let's say 70. So someone who has 100 in maths will most likely have like 70, is it 79 or 70 rather in physics. So this is like modeling your data actually. So, and it's linear regression is so simple but quite powerful. All right. Okay, so let's talk about probability density functions and cumulative distribution functions. Okay, PDFs and CDFs. So here we can compute probability density function and cumulative density distribution function for various distributions. So all of these, they have formulas, right? So sometimes you have to integrate to get things, or differentiate sometimes to get some of these things. So again, here we have a sample. We are taking values from -5 to 5, and we are looking at 100. We are spreading it out in 100 possible divisions, right? So we are getting the PDF values in line 6 and 7 as PDF values in line 6. So you see norm.pdf and all that, and then you have the CDF values That's the cumulative distribution function. That's num.cdf, and then you're printing out those values here, basically. So, but X is the key thing here. So it all depends on the range over which you're working. So you can see the PDF values now. They are also, you can see it's from -5 to 5. If you check the values, yeah. So you can see that that's what we have here. So the PDF now is normally distributed to, like you can see, based on those values. So you have the CDF values also, as all of that go by. Okay, so let's talk about multivariate distributions and tests. For instance, you want if you want to generate samples and perform statistical tests. So here we have mean 0, 0, and we have covariance 1. Yeah, this is a covariance matrix 1.05051, like that. And then we have MV normal, which is multivariate normal distribution, which we want to do. So that's multivariate. The keyword here is multivariate underscore normal. And then with that, the mean and the covariance you have, and then you put your samples here, and then you can generate the samples like that as that appears. So of course, I mean, for those who really understand it, you can relate with it. So I mean, all the ideas may not be useful for you depending on your field, right? But if you are statistically inclined, you can find them quite useful, especially if you already understand the theory behind these things. So this becomes very useful for you. So non-parametric parametric methods, right? Like kernel density estimation is one thing we can do here. So you estimate the probability density function of a random variable. So here you are generating the data randomly of size 1000. And then for the kernel density estimation, you're using the Gaussian kernel density estimation on the data. And then you are generating an X grid between the minimum data and maximum data based on whatever you have from 4. And, that is divided into 100 equal parts. Then you can get the estimated density to be kd.evaluate whatever X grid you have here. And then you can generate the data, get the X grid and the estimated density, all of that. And you have your values in just a click, So so it's a lot, right? Because it's 1000. So yeah, the estimated density is the last thing. The X grid, you have that here and all that like that. So let's talk about statistical tests and measures. Statistical tests and measures. For instance, you need the goodness of fit tests. So you want to test if data follows a specific distribution, e.g., if it follows chi-square test and all that. So you say from SciPy.Stats, import chi-square. Chi-square is basically used for categorical data, so for grouping. So, and there you have to worry about the observed data and the expected data. Let's say the observed data is 10, 15, 8, 12, and 5, and the expected data is 10, 10, 10, 10, 10, like that, And then you want to do the chi-square thing to decide what it looks like. And the p-value tells you a lot of information about that, all right? So the chi-square stat gives you 5.8, and the p-value is 0.214. So it's greater than 0.05. So I think you're going to reject the null hypothesis or something. So which means that there's significant difference between the observed and expected. So it doesn't really follow chi-square test or something. So don't forget to confirm, the rule for whether it's less than 0.05 or greater, right? Okay, so let's talk about spatial statistics. So like under spatial statistics, we talk about point pattern analysis. So analyze spatial distributions of points, e.g. nearest neighbor analysis. So here you have the keyword is point by serial R, So the data is also randomly generated 100 points, and the binary data is now np.random integer. So now you have integer, like you want the number to be integer, and then you now have the correlation and p-value from the points by serial R of the binary data together with the original data, and then you can print the correlation and p-value. And of course, again, the p-value helps you to make decisions. So again, the p-value here is greater than 0.05, and you can make your decision based on that. So of course, most of this will make sense to you if you already have a statistical background, if you already know the theory behind all of these things. So the computation part will be very sensible to you. And then, of course, all of these are very powerful in making decisions, in testing hypotheses, comparing data, and things like that. Thank you so much for listening. If you have not subscribed, be sure to do that. And of course, hit the notification bell. And of course, always comment, like, and share. As I see you in the next video, we'll be talking about SciPy Interpolate module. That's another very interesting one. There you can talk about, you can even work on pictures. If I have an interesting example where I work on one of my pictures using that module. Thanks for listening. See you in the next one.